presentation. Okay, the people online, can you see it nicely? Can you see the slides?
Yes.
Perfect.
Everything okay?
Right, wonderful. Oh, I started from the end. Let me get to the beginning. So, this is currently we are going to present SweetAda. It's Gabrielle's work. I will be here just helping him doing some demonstrations on programming boards like FPGAs and things like that. And yeah, here we go. So the goals for this presentation are basically to showcase what SweetAda is to you, the wider Ada community, and how to work with it. And the way we are going to do that is both through the slides and the actual demonstration here with some code. So, do you want to explain where you got started?
We can start explaining SweetAda as means of implementing Ada on the widest possible range of system. And here we have the issues that I have to face once I start the project. We have a lot of CPUs and a lot of platforms. Platforms are maybe those boards, and every of the boards have its own implementation in the Ada file system. We can see maybe something on the PC, or you can go on.
Mm-hmm.
Okay. SweetAda try to be auto-consistent. There is no need of an underlying operating system, and I tried also to avoid to use, where possible, the compiler library, that is the libgcc. It is meant also to be used without complicated tools. Basically, SweetAda is a build system which is based upon the GNU Make. There is two builds mode, one with the GPR build and one with the classic GNAT Make, which is included in the standard toolchain of the FSF. Okay.
Also, I just wanted to mention, he's the author, I'm just a user. One of the nice things is that you can, there are configuration files for each platform, so those are also easily configurable, and you can add some scripts, or some already have some scripts written mostly in Python or Shell, so that you can automate some tasks like uploading programs to boards, or just debugging them, like with OpenOCD, if you know what that is, for RISC-V, etc., etc. So it's quite flexible. It's very, very nice.
Yes, maybe we can see we can start with demo on the board, so we see practical example, because we have in time shortage, so it's better to concentrate on the practical views of the system.
So
maybe in the meantime, I will try to explain how SweetAda works.
And if you want some like guide, quick, simple guide on what we are going to do with some documentation need for like some examples that we are going to run, you will have the slides here, and you can just follow the step-by-step sections that I've written, like build the RTS, because obviously SweetAda has its own runtime system. Select the board, the configuration flags, etc. and then you can just follow it at home if you want. However, since we are here live, we are going to try to do things as we move along. So we can switch computers.
I will skip philosophical reasons that stay behind SweetAda. Maybe they do not even exist. SweetAda is conceived as a means to run Ada code, and there is no clear purpose. Basic concept that I want to implement was the possibility to implement Ada on the widest possible range of hardware. We can view the Ada file system here. Yes, okay.
So just to let you know, this is basically a Git clone of what you will get. So if you copy the repository, you get all these file systems and folders and
more or less is a direct clone of the repository. There is just a bash shell script in order to ease the demo. The layout is quite standard. You can recognize some normal directory names. One of the most important parts of SweetAda is the core hierarchy. Here you can find the basic units needed to implement low-level details. There is the bits unit. Okay. You can find basic types declarations, bit fields, arrays, little endian and byte endian conversions, and functions, subprograms really, for handling very low-level details like shift, arithmetic rotates, and so on. There is the LL utils unit. You can find byte swap conversions driven by addresses instead of objects, and utilities for handling addresses and bit fields inside addresses, conversions between similar types, and something like atomic types for synchronization primitives, and so on. There are a lot of units, and I would like to highlight some important aspects of the core complex hierarchy, because it is CPU independent. Nearly every subprogram is separate, and nearly every unit has pragma no elaboration code. So you can call subprogram in this unit directly from machine language. Okay. Indeed, the various subdirectories are sets of separable subprograms. For example, here we have the separate implementation of bytethreads. Why subprograms are separable? Because you can implement your own code by simple write the correspondent file in your directory, in the platform directory. The build system automatically will compile your file instead of the standard one. Okay. Then we have the CPU's hierarchy, which covers all the low-level details of every CPU. Here we have the x86 architecture with with infamous selectors and GDT tables. This is for the x86. Then we have
and also I wanted to note the amount of architectures that are currently supported. Not all architectures are as developed and as tested as others, but for example, the x86, the HR64, the RISC-V architectures can do already support like multi-CPU execution environments. So we'll get to that.
In a very simple way.
Yeah, very simple.
It's not fully exploited.
But you can get, like, for example, some already subroutines to print characters in some less developed architectures, such as like PowerPC or Spark. So this highlights the flexibility not only of the framework, but also the compiler and the toolchain that's currently available in the open source world, basically.
Okay. We have to speed up, so otherwise we can't afford to show everything. So the build system of SweetAda is conceived like a chain of configuration files. The main configuration file is in the root directory. This is as a matter of fact, every dot in file is a configuration file. This is the main configuration file. Here you should fill prefixes and directories of your toolchain. This is the Windows case. The MSys2 case. You have to fill the so-called toolchain prefix. That is the directory where you can find compiler, executables, and so on. Do not put double quotes because they are automatically discarded by the system. This is the macOS case. You should fill in also Python interpreter and maybe the TCL interpreter. These are the standard the so-called toolchain triplets from the GNU world. Okay, if you get the I don't know, the RISC-V compiler from Adacore, chances are that it is called RISC-V32-ELF. Okay, the prefix should go here, and the name should go here. Obviously, I have all the tool chains because I have to develop in every platform and every CPU. You have to fill in only your tool chain. This is the build mode because there are two build modes in SweetAda. The standard mode is by means of the GPR build utility. To be honest, I prefer the GNAT-make because it seems to me it has many problems, is a little bit faster. This is a flag to check that every tool is online. This is a flag to check if you want to use the ELF tool, which is a utility inside the libutils directory. This is the other mode, which is stuck at 22. This is the type of the runtime. SweetAda has two types of runtime, and we have a zero footprint. It is really a zero footprint. We do not have a link with the library. And there is the small footprint, which has a little bit of features like image attribute handling, floating point handling, and so on. This is then there is the optimization level. You can set it to 1, 2, 3. This is something like the -O option in the GCC compiler. This is the main configuration file. You have to configure it, I think, only once, because you have not to touch everything else. What it is more important is the platform configuration file, because it contains the configuration of your hardware. You can find it in the platforms hierarchy. There are all the platforms that I more or less developed. For example, you can choose the PCX86 just for a change. The configuration file is here. Okay. No, sorry. PC86 is one of the platform which have a sub-platform configuration. In every directory with a name like platform-something, you can find the real configuration, which will be symlinked in this directory at configure time. For example, you can see at the QM-ROM, here it's okay, open webpage. This is the real configuration file. We want to use the C library because we have a C library inside SweetAda. You might ask why we have a C library, why we need a C library. We don't. We have a C library only for the purpose to port, as an aid to port an existing software. Indeed, many of the subprograms, of the functions, of the C-style functions in the C library are just wrappers towards ADA subprograms. We can see the C library is here. Okay. You can recognize the standard headers of the system. And for example, the string header is the header which contains memory block routines. Is just an implementation of ADA subprograms in the core hierarchy. If I am not clear, just 10 minutes. Sorry, it's a big problem. So we turn. Let's try to create a virtual target. I want to use the QEMU as a target. So,
and I have to mention while Gabrielle is typing and building everything that we have support for physical boards, as you will see now in just a second, but also for many virtual targets. You can find them in the platforms. There were several entries for QEMU, QEMU RISC-V, PowerPC, x86, etc. So it helps with the development speed to test things. So what Gabrielle is doing now is he's selecting what platform he wants to target, what sub-platform he wants to target, in case there is a sub-platform. In this case, there is the QEMU ROM sub-platform for PC x86. And he's going to execute the create kernel config. That is going to take the files, the configuration files, the setup files, and it's going to, as he said earlier, link them into the top directory. So that now SweetAda will use those to compile the final code.
Okay. You can see that okay. You can see that the file system changed because files from the sub-platform are just SYM links into the sub-platform's files. This target of the GNU make is just to create a kernel.cfg file which will drive every step of the compilation. Okay, at this point we have no built nothing. Okay, the next step is to configure really the system. We have not to specify the platform anymore. The system knows that already. So the step is to configure the system.
And what was just printed to the screen, you can modify it with make flags if you want, in case you want to run a test with a different optimization variable or with some value change like the RTS. Instead of the 0 footprint, you want to test the small footprint one without having to manually change the configuration file and then undo it if it doesn't work. You can just do it in the command line directly.
Okay, so the SweetAda build system has just read this file. These are normal GNU make assignments. Here we can find the GCC compiler options. There are many. These are commands to manage the physical running of the target. you can find these values also in the output of the configure step. Okay. We have use SweetAda at yes, which means that we are going to call a C program in a foreign library. This is the smooth. We want to use the smooth footprint runtime and so on. So we actually compile the system.
So make-call will compile the kernel, the binary that's going to be uploaded.
Startup.s and llkernel.s are standard names, but you may want to change to everything you want. Just specify them in the configuration file. Okay. And so we are ready to run.
And this the make run will use the helper scripts to do whatever you want them to do. If it's to set up a virtual target or upload it to a board, whatever you need.
This is the VGA screen of the emulated PC, and these are the two serial ports, the COM1 and COM2 output. Okay, this is something like an hardware dump of the platform. We have PCI device and so on. The PC x86 is one of the most evaluated platforms in SweetAda, since we can even ping it because there is a little NE2000 driver. So I am going to ping the target. Okay. You can see there the ICMP sequence in the TCP/IP stack, which is very, very small. So we have to speed up. Sorry. We can switch to physical platform.
Yes, if you want to do the onboard.
Okay. Now I switch to Windows. This is an ARM Cortex M0 platform. The name is FRDM KL46, something like that. Okay, it is driven by SWD cable in OpenOCD. Okay, so the steps are the same. We want to create a platform target.
Once again, create kernel config just to generate the configuration for the target.
I am using the MinW32 make from the MC's distribution, but you can use your new make in the libutils directory. There is a porting of the I think 3.80 version of GNU make. I think it is an static executable, so you have no problem running it. Okay, the configuration file is correctly created. We can configure. We can skip the configure phase. We can run directly the whole target. The configure phase is just to have something visual in front of your eyes. These are libgcc files, startup files in machine language, the core implementation, and your platform's files. Okay, so I can show the configuration of this platform. I don't know.
If you want to run it, because the Q&A time should be now, so it would be best if you...
Do you want to...
Oh, we can do it first, if you want.
Just one moment. Okay.
So, for example, now we are showcasing the debug capabilities. There is a debug target in case you want to not only run your program, but also debug it. This will require you to write some custom scripts because each board requires their own setup and tools and everything. But this is also one of the goals of the, for the project.
The target now is stopped at reset. And we can start it and put a breakpoint near the setup. Okay. So I am not able to find the configuration of this platform. I don't know why. Sorry. In the meantime, you can show.
Well, it's questions and answer time already. So if you have any questions, if not, one of the things we wanted to show you, this is not a CPU. This is actually an FPGA. So SweetAda is flexible enough to just target whatever you want. So what we can showcase, if not now in the break, if you are interested, is we can upload a RISC-V CPU here, the NeoRV32, which is written in VHDL, and it's actually simulated and compiled with GHDL, an ADA program. And we can run the timers here, we can run the LEDs, UARTs, and receive messages directly from an FPGA, just to showcase how flexible it is with just a couple of commands.
Okay, sorry, I finally found the file. Okay, this is the configuration of this platform. You can see all the assignments to specify what kind of board you are going to create. Okay. You have the ARM in the CPU's directory. These are options, the compiler, and you can fill directly here the commands towards the OpenOCD server, which is running here. Okay, and which is driven by the software here. Okay, the target is now stuck in a loop in application.adb. We have a main loop LED and an interrupt LED, which fires at 1 kHz. Okay.
So if you have any questions or if you would like to know more, if not, we don't have that much time, but once again, in the break, I can show you how to run SweetAda in this FPGA with literally 2 commands. So very simple stuff, very nice stuff. My recommendation is take a look at the source code. You will see there are plenty of functionality. There is plenty of functionality for nearly any board, and it's very easy if you have a board that's not supported to just copy paste some files, change the values for your specific platform, and then just run. That's exactly what I did with this FPGA for today, and it took me like a week to get it started and just a few hours each day. So great stuff.
Sorry, the documentation is very outdated. I make the promise that I feel important piece of information as fast as possible. Okay.
And once again, you have the slides. If you want a guide, a step-by-step guide, what would need to be done to get something compiled, you can just read them. We skipped over them since we were going to do them live, but they are documented there if you want. So, any questions? Alex?
So I have never dealt extensively with cross-compiling or compiling for this kind of platform, but what I see is that people has a very bad time bootstrapping GNAT for other platforms, new versions from old versions, and so on. So what's the trick or the secret sauce to have so many platform support and everything that is problem?
Let me repeat the question so that the people online can understand it. So the question is, how can so many platforms be supported at the toolchain level, since GNAT is fairly difficult to bootstrap and compile new and varied versions? So
I really don't know. One of the reasons of the existence of SweetAda is just to try to not break open doors. So to have the most widest range of platforms is an help to make a better system, because in this way, I had the opportunity to develop, for example, a core system which is CPU independent. This is one of the reasons. Sincerely speaking, there are no other explanation.
I also would like to say there is a folder that we didn't cover known as toolchains, and there are a few scripts. They are not automated. You would have to manually download and modify some values, but they are designed to very quickly compile several different toolchains for several different architectures. Once again, not fully automated. You have to download the files manually. You have to get things set up, but there is some support to help you quickly get started.
In the toolchains directory, you can find some bash shell scripts. Once you download the official source code from the new repository, you should be able to create a complete toolchain. Images, BCC, LGBT. Now, tools is a little bit complicated. This is for people that want to use GPR build, but the fact is that GPR build is not able to cover some types of toolchains. So this is an hack. This is and a utility script. If you run with the proper, you can change the version of the software because
the time. So if you have any questions during the break, obviously feel free to come to Gabrielle. Feel free to ask any questions. He also has an FPGA if you want to see it running also with the RISC-V CPU NeRV32. So,
I'm sorry, but I think a whole week is not sufficient to cover every aspect of the system.
So as a user, I would like to thank Gabriel for his work. If you go into the GitHub, you can see he has over 2,500 commits all by himself. And he has basically built this thing up from the ground alone. So yeah, impressive work from my side. So thank you very much, Gabriel. So what I've just connected is the ULX 3S, and I'm using the Virtex framework to rapidly compile everything. Virtex is just an open source framework that you can quickly use to work with a lot of FPGAs nowadays. So it makes the setup very easy. You don't have to install these huge tools from Xilinx or Altera or things like that, and they are pretty easy to work with. So I have a build script just to help myself a little bit. So this script would actually be the full thing just to compile everything from source code into the FPGA. In case you don't know, you don't program FPGAs. You offload a bit stream to them that reconfigures the electronic circuits there, so you can implement whatever logic you want. And in this case, we are implementing the Neo RV32 CPU, which once again, it's written in VHDL, and it's using the GHDL compiler, which is written in Ada. It's one of the largest open source projects written in Ada. So I won't do the synthesis now. The NeRV is a very small core. It takes about 5 minutes to get compiled, everything. Some larger systems, which I've tested with Ada too, can take a day to compile. They are multi-core, Linux-capable systems, so fairly powerful ones. I've been able to run Ada on Linux on this little device with 32 megabytes of RAM, so that's good. So I've already done the synthesis. I won't be doing it now. So, but what I want to do is just to source the environment so that I have the setup that I want. So first one done. Then the first line is just to get the FPGA tooling ready, and the second one is to get the build system ready. And what I will do now is just simply copy these two lines, and instead of building everything, which is the instruction I have here, and loading it into the FPGA, I will only load it because the build has already taken place. Once again, it would take 5 minutes in this case, but I don't want to waste my time. Oh, I connected it to the wrong USB port. It has two USB ports. One is for data, one is for actual programming. Now the computer recognizes. Okay, now it's programming the thing. It takes a few seconds. I will show this. Let me show the people here the board, which is connected. And this is just the LEDs that are indicating that it's being programmed, and I'll show you later what it works on. Sorry for the wiki setup for those online. I will try to improve it after the break. Sorry for that. And we are done. So that you can see it, it's now the FPGA. You have like a rainbow thing going on. That's the actual code of the FPGA. This is the electronic circuit. This is not SweetAda. This is nothing like that. That's the initialization procedure and the bootloader and fancy things that are happening thanks to Virtex, which I will not explain. But now we can go into build, SweetAda, and I want to add GPR build to my path. This is just to show you that you can add any toolchain that you may want to with SweetAda. I'm using the earlier provided ones because I like them. So I'm going to use RISC-V toolchain because NeoRV32 is a RISC-V CPU. Now they are all set up. CPU. So I'm going to create the small footprint with the toolchain for RISC-V and the RTS.
This step is necessary only
once. Yeah.
Only once, the creation of the runtime, because once you create the runtime, it remains in the file system, and it is usable by every toolchain, by every target which are using a RISC-V CPU.
Mm-hmm. And now I will, now that I've configured the CPU, the RISC-V 32-bit one, I want to select the board I'm actually going to work with. So that's the NeoRV32 with the sub-platform of this little FPGA. This platform actually supports quite a few different sub-platforms because each one has a different configuration.
If you don't have a physical platform, there is the GHDL sub-platform, which is based on the GHDL compiler. So you can test it in virtual mode.
Okay, so for example, by default, the toolchain prefix will be OPT as an external build toolchain. I'm not using that one. I'm using the ones I've provided. So let me just change that path. So okay. So I'm going to run the full thing, and instead of, as Gabrielle Galeotti showed you, you can change the values of each configuration file so that they automatically use whatever you need. As I said, you can change them also from the command line in case you want to test a different toolchain or a different configuration only once without making it, having to type it into the actual file and then reverting the changes, etc. So here is a showcase on how that would be done. I'm changing the toolchain prefix, the GPR build prefix. I'm using the GPR build mode in this case, and I'm going to run the thing. Let me change, sorry, the platform to NeoRV32. That sub-platform. I was testing the QMO one before, so LX3S Virtex.
What you are in the configure phase?
I did run the configuration, right? Yes.
Okay. Make all.
All. Oh, I didn't change. Sorry, the toolchain prefix. Prefix, but that has been changed. Oh, sorry. I need to run the configuration with this. And now I can run it.